Okay, thanks, Tony. Okay, so today we will start our tutorial with a tutorial question for combined loadings. We have two questions today. This is the first one. We have a column under applied load B equal to 40 kilonewton, and this column is fixed at the base, and the cross section of this section is of this column is square hollow section as shown, and the requirement is to find the maximum compressive stress in the column. Okay, so we will now shift to the bend to explain this to you. So our tutorial today will be about the combined loading or combined stresses. Okay, as you remember, we before studied the normal. We have studied the normal stresses, sigma, and if you remember, we have two types of normal stresses. Normal stress due to normal forces N, and we can call this sigma N. And the other type is normal stresses due to bending moments M, and we call this sigma M. So we have sigma M and sigma N. Okay, this is a type of normal stresses. If you remember the formulas for each one, sigma N was equal to the normal force divided by the area, and this may be positive or negative. This will be positive if the normal force is tension force, and this will be negative if the normal force is compression force. Okay, for the moment, the formula for sigma M equal to M divided by I multiplied by Y. If this mx, so this ix and this y. And if the moment is about y-axis, so we have my divided by iy multiplied by x. Okay, where I is the inertia about x, iy inertia about y, x and y are the distance from the centroid CG to the point of stresses, and also x is similar, but in x direction, distance from centroid to point of stresses. Okay, and m or my or mx are the applied moment. These are the general equation for sigma n and sigma m. Okay, we can explain this with illustration figure. For sigma n, again, n by a, positive or negative. If we have a cross section, this is our cross section. Okay, if we have this our cross section here, and we have applied force in the CG here, this normal force may be acting, pushing the section, or maybe pulling the section. So if it pushing the section, this type, so it will be compression, and the sign will be negative sign. If the force is pulling the section, so this means that the force is tension force, and the sign is positive. Okay, so this is for sigma n, and you remember that A is the cross section area. If this B and this T, so A equal to B multiplied by T as example. Okay, for the moment we have sigma M again equal to M x divided by Ix multiplied by Y, or My by Iy multiplied by X. If we have moment, this is our cross section, and we have this X axis and this Y axis. So if the moment is rotating about X axis, this Mx, so the formula we will use is Mx divided by Ix multiplied by Y. And where is Y? Y is the distance from the CG centroid to the point of stress. If we want to calculate the stress at point 1, so this will be Y1. If you want to calculate the stress at this point 2, so this will be Y2, and so on. Okay, and as you remember, or as you know, this moment is causing tension in one side of the section, at one side, and causing compression at the other side. So this is the tail of the section of the moment, so it's causing tension, and the head of the moment causing compression. So this is MX case. If we have same cross section, rectangular cross section, and this is X axis, and this is Y axis. So if we have the applied moment in this direction, so this means this My, because it is rotating about My. Okay, and this is our CG. So if this My, so the formula we need to use, sigma for moment, will be My by Iy multiplied by X. And where is X? X will be the distance from the centroid to the point of stress. If you want to calculate the point of stress here, point 1, so this will be X1. If you want to calculate the here or here, so this will be X2 or X3 and so on. So if My, so the distance will be in X direction. If Mx, so the distance will be in Y direction. And here as well, the moment causing tension in one side and compression in the other side. So this side will be under tension and this side will be under compression. Okay, this is like a summary for what we have studied before, if we have normal force and if we have moment. And now if we have a combination between normal and moment. So this is our topic today. So if we have combination of N and M. So if we have M and M, so we have sigma M and sigma M. And our formula will be sigma equal to sigma N plus sigma M. And should be N divided by A plus or minus M by I multiplied by Y, if this mx. Or you can replace this with my by iy multiplied by x if we have my. Okay, so this is our general formula. I will write it again here. Sigma equal to n divided by a plus or minus m I y. Okay, here we will have one of the two signs. This may be positive or negative. Again, this is positive if the force, normal force, is tension, and negative if the normal force is compression. But here we will, for moment and mx or my, we will use both signs. It will be positive and negative in the same time. What does this mean? This means that if we return back to the previous slide or the previous draft, if we have cross section and we have moment mx, so this mx, and this is our centroid or CG here, this moment will cause one half or one part of the section to be under tension. The green part will be under tension, and this yellow part will be under compression. So when we apply moment on a section, half of the section or part of the section will be under tension and part of the section will be under compression. But for this is for moment. For normal force, if we have section, it cannot be tension and compression at once. If the force is compression, so all the section will be under compression, not half or not part. And if the section under tension force, so this means that the whole section will be under tension force. That's why our general equation will be N by A will be depending on the direction of the force or the sign of the force. But for moment we will use both positive and negative. This means that we have two equations for stress, sigma 1 and sigma 2. Sigma 1 will be N by A plus mi m divided by I multiplied by y, or N divided by A minus m I y. So this equation for the part of moment under tension or the tension side of the moment tension side, and this equation will be for moment under in the compression side. Okay, so this is our formula for the combination, because the moment causing tension and compression for at the same time, but the normal force only causing either tension or compression. Okay, do you have any problem in the formula? Okay, so the second step, the second parameter I need to show you or I need to explain to you is the stress distribution over a section. Also need to know this one. Stress distribution means if we want to draw a graph or a figure for the stress over the whole section. If we have normal force due to normal stress due to normal force N, the equation N divided by A may be positive or negative. Positive if tension and negative if compression. So if we have section and the force is tension force, the stress sigma n will be n by a. Okay, and if we want to draw a stress distribution, so we will have like a guidelines, and we will have a datum. This datum may be parallel to y, if this y axis, and this is x axis. So this datum, this is our datum, may be parallel to x or parallel to y, doesn't matter, because the normal stress is uniformly distributed. Okay, so in other cases I can draw the datum in this direction, so it doesn't matter. Okay, so now if we plot the value of stress, so the value of stress is constant, and this value is called sigma n equal to n by a. If the force tension, so this is positive, and we can put positive sign here. And if we want to draw it in this direction, I will put it above the datum because it is positive. If we want to draw it in this direction, it's okay as well. This tension and this sigma n equal to n divided by a. Okay. The second case, if this force is compression, like pushing the section. If the force is compression, so we will write another datum here and another datum here. So this is our datum. This stress will be in this direction because it is compression, negative, and sigma n equal to negative n by a. If you want to draw it in this side, so this is our datum, and this is the stress, negative sigma n equal to n by a, and we put negative sign. Okay, so this is the stress distribution for the normal force case. And if we have sigma moment, sigma m we said before equal to, if we have mx divided by ix multiplied by y. And we said this value is positive and tension. So if we have a moment here over this section, and this is x-axis and y-axis, and this is our moment mx. So if we have mx, so our datum should be parallel to the moment. Here the moment is controlling the datum, or is controlling the stress distribution. So datum is parallel to the moment. So if we have mx, so the datum will be vertical datum. This is our datum. Okay, and this is the neutral x. So how can we plot this this value here? This value is here is will be sigma m equal to negative mx by ix multiplied by y, and the other side will be same value but positive mx by ix multiplied by y, and we connect them with a straight line. Okay, and this side is under compression and this side under tension, because as if we return back to the previous slide, we said that the moment has the head of the moment causing compression and the tail of the moment causing tension. So this half of the section is under tension, and the other part or the other half is under compression. And we can represent this using this figure, the stress distribution. Okay, so this is the stress distribution if we have mx. And the third step, if we have my. If we have my, so the stress sigma m will be positive or negative my divided by iy multiplied by x. And this is the same cross section, and this is x-axis, and this is y-axis. And if we have my means moment about y, so this is my. Here the datum again should be parallel to the moment, so our datum, this is our guidelines, and this is our datum. And here we have value here of stress sigma m equal to positive my by iy multiplied by x, and the other side will be same value but negative sig my divided by iy multiplied by x, and we connect these two values with a straight line. So this will be positive and this is negative, because we said before this moment this side will be under tension and this side will be under compression. So this half is under tension and this half is under compression. Okay, so this is the stress distribution over cross section due to M or N. Now if we have a combination between M and N, if we have sigma equal to NA by A plus or minus mx by ix multiplied by y. How can we do this? If we divide it to two parts, just to illustrate for you, this is our cross section again, and this is x-axis, y-axis, and we have normal force in the middle, compression force, and we have applied moment mx in this direction. Okay, if we want to draw the stress distribution for normal force, so we will have datum, and the stress will be negative n by a constant over the section. So this is stress due to normal force. Due to moment, we have vertical datum as well. This moment is causing tension in this side and compression in the other side. And the value is mxix multiplied by y. So we will put this here, negative mi multiplied by y, mxix multiplied by y, and the other side same value but in a reverse direction, or positive mxix multiplied by y, and we connect them together with a straight line. This under compression and this are under tension, because again this moment causing tension in this side and compression in this side under tension and this side under compression. Okay, now if we want to combine between sigma n and sigma m, what we will have? if we have combination, if we want to make the combination, if you want to make combination between these two, it depends on the value of this and this value. Okay, but if we do it like mathematically, we will have three options or three probabilities. Okay, the first probability, if this value n divided by a is larger than mx by ix. Sorry. Uh, Return this value here. Okay. Now, if we want to like sum these two together, we have these two negative values. So we have the first option here. If we sum these two together, so we'll have a bigger negative value. So we will have negative n by a, negative mx ix y multiplied by y. Okay. But the other side, we have two of this positive and this sorry negative, and this is positive. So if one is greater than the other, so the sign will be convenient, or the sign will be the we will take the sign of the bigger value. Okay. So the first case, if negative n by a is greater than mx by ix multiplied by y. So the result will be a small negative value. Okay. And we connect them together with a straight line, and the whole section will be under compression. So this is our first probability. The second probability, if we have NA, negative NA is smaller than MXIX multiplied by Y. So this is our datum. The top value will not be affected because they are negative, because both of them are negative. So just sum them together. But here, if the positive greater than the negative, so we will have a small negative, a small positive value, negative n by a plus mx ix multiplied by y, and we connect them together with a straight line. So we have this compression, and this small part is under tension. So the first case, if the compression greater than the tension, so all the section, whole section will be under compression. The second probability is if the positive greater than the negative, so we will have small positive value at the bottom side. The third probability, if they are equal, NA is equal to mx ix multiplied by y. What does this mean? So this will be our datum. The top value will not be affected again. NA negative mx ix multiplied by y. But the lower value or the bottom value will be 0 because they are equal. So this is our stress distribution here, and the whole section will be under compression. Okay. So in any problem we may have three options, but one of them only will happen. So this only because we are dealing without numbers, so we may have three options. Okay. Do you have any problem with this equation or stress distribution? Okay, so now return back to our problem. So if we have this problem now here, this is our problem. We need to find the maximum compressive stress in the column. Okay, I will start with this one now. So our first tutorial question today, we have a column, vertical column. This column is fixed, and we have applied load B equal to 40 kilonewton here, and the width of the column is 150 millimeter, and given this is x-axis, z-axis, the cross section is a square hollow section. This is the square hollow section given. The outer dimension is 150 millimeter, and given that the thickness of the hollow section is 5 millimeter, this means that L outer is 150. So L inner, the inner dimension will be 150 minus 2 multiplied by 5 give us 140 millimeter. So the dimension inside 140 by 140 millimeter. Okay, and also given that this is x-axis and this is y-axis, the requirement is to find the maximum compressive stress on the column. Okay, as you know, the maximum stresses in this column will be at the base, because the column is supported only at the base, so will be at section AA. And the section at AA, because the column is uniform or regular, so this is our cross section at AA. Okay, so for this problem we need to first step to know what is the straining action, or what is the applying forces on the column. So the straining action for this column are normal and moment. Okay, because if we look at the cross section, this is our cross section, and given that we have a small applied load here, sorry, B equal to 40 kilonewton, and this is the section, and this is x-axis, y-axis. So this force B is normal to the cross section. So this force is normal force N. So first of all, we know that B is causing normal force or normal stresses in the section on the section. Okay. Another information from the question, that the force B is eccentric force. What mean by eccentric force? If we have a cross section, so if the load is applying at the CG, this means that the load is concentric load. Okay, but if the load far from the CG, if this is the CG and the applying load is somewhere here, this means that there is a distance between the CG and the load E. This means that the column is eccentric, or the loading is eccentric loading. Okay, concentric loading, so only the force is applying or causing stresses on the section. But if the column has eccentric loading, what this mean for us, or how can we deal with this? For eccentric loading, here if we have an eccentric load here, it's y, x, we can deal with eccentric loading as to make it simple or simplify the case using the static simplification, that we can transfer this load B to the CG. So we will applying the load instead of out the CG, add the CG, but we need to also add moment due to this transfer. Okay, so to move a force from a point to the CG, we need to apply the load and additional moment. This moment M will be in this direction. This moment will be equal to the force B multiplied by the distance we transfer E. So if this E, the distance is E, so the new moment will be B multiplied by E. Okay? And why I put this moment in this direction? Do you know? Are you still here or are not listening? Ching and Tony, are you here? Okay. Can you understand what I am saying now? Okay. Okay, again, I'm just trying to deal with this eccentric loading. We need to move the load to the centroid or the CG and adding moment M. This moment M equal to the force B multiplied by the distance E. Okay? This moment is My because the load is acting on x axis, so there is no eccentricity with x. So this moment will be about y axis. Okay, and because I assumed that this load is pushing in this direction, so the moment will cause compression in this side and cause tension in this side. I mean that this half or this part will be under tension and this part will be under compression because the force is pushing in the right part or the right half. Okay, so for our problem now, we need to find N and M. We from the equation or from the problem, the question, we have that N equal to B equal to 40 kilonewton. But for M, again, this is our cross section and the load is here, B equal to 40 kilonewton, and this is axis, X and Y axis, and this is our centroid. So the distance from the load to the CG is this distance. If this all 150 millimeter, this means that will be 75 millimeter. So for our problem, given E equal to 75 millimeter, then the moment or the additional moment we need to add is B by E, which is 40 kilonewton multiplied by 75 millimeter, give us 3000 kilonewton millimeter. In kilonewton meter will be 3 kilonewton meter. Okay, so this will be equivalent to the cross section and we already now transferring or moving the load to this point. So B is acting now in this point, B equal to 40, and we have another additional moment My equal to 3 kilonewton meter. Okay. In other questions, he may give you the cross section like this to be easier for you. Okay. So now we know that we have M and N. So the stress or the combined stresses will be sigma combined equal to sigma N plus sigma M, or negative N by A plus or minus My divided by Iy multiplied by X. So this is our formula. Why I put negative sign here? This negative sign because the applying force B is compression, so N by A. So the force N is compression. Okay. Before we start, we need two parameters to calculate before starting the substitution. The area of the section will be the outer area 150 square minus the inner area 140 square. Give us that the area is 2,900 millimeter square. The inertia Iy, and because this is this is a square, so Iy should be equal to Ix equal to 150 to the power 4 divided by 12 minus 140 to the power 4 divided by 12 give us that the inertia will be 1 multiplied by 10 to the power 7 millimeter to the power 4. Okay, so this is the inertia and the area. Now we can substitute in the formula. So sigma will be negative 40, and we said before all the units should be Newton millimeter. So negative 40 multiplied by 10 to the power 3 divided by 2,900 plus or minus the moment 3 multiplied by 10 to the power 6 to convert it to Newton millimeter divided by I 1 multiplied by 10 to the power 7 multiplied by X. What is X? He asked for sigma max. So M max should be corresponding to X max. What is X max? X max is the farthest distance from the centroid on the section. So if this is the centroid CG, so any point on this line or this line will be the maximum stress. Okay, but because the moment is causing compression in this side and tension in this side, so the compression, the maximum compression will be expected in this area. Okay, so X will be the distance from here to here. X is 75 millimeter. So I will put X as 75 millimeter. This gives us that sigma will be, sigma N will be negative 14 MPa or Newton per millimeter square, plus or minus for the moment 22 Newton per millimeter square. So sigma 1 will be negative 14 plus 22, and sigma 2 will be negative 14 minus 22. This gives us positive 8 Newton per millimeter, and the positive sign means this part or this point will be under tension, and the other side will be negative 36 Newton per millimeter square, and the negative sign means that this under compression. So sigma max compressive or sigma compressive strength will be negative 36 Newton per millimeter square. Okay? Do you have problem in this question? If you want to sketch the stress distribution for this example, okay, thank you, Singh. If you want to draw the stress distribution here, so if this is our cross section, okay, so the stress distribution due to normal force will be, I will put it in this direction, negative sigma n, which is this value, negative 14 MPa. Okay, for moment, here this was the moment, so tension in this side, compression in this side. So here we will have, and we put this value, so 22, and here negative 22. So this positive and this negative. So this sigma m and this sigma n. So the combination or the final stresses, I put it here. In this side, negative 14 plus 22 give us positive 8 Newton per millimeter square. And this side we have negative 14, negative 22, so we have negative 36 MPa or Newton per millimeter. And we connect them together with a straight line. So this is negative and this is positive or tension. This tension and this compression. Okay. Do you have any problem in this one? The question now is why I put the stress distribution parallel to x, because again I said this is y axis and this is x axis. So what controlling our datum is the moment. So our datum should be parallel to the moment, and as we have our moment my, so the datum should be in x direction. So the stress distribution, the final stress distribution is as this figure. Okay. So now we can return back to the tutorial. Now we finished problem 1. Now we as our turn to go to question 2. This is question 2. Now for question 2, we have a beam, simple beam, AB, supported by hinge at A and a link member CB or BC, and we have applied load Q equal to 10 kilonewton per meter, and the requirement is to Find the maximum tensile stress for member AB. If the section or the cross section is square hollow section, so the section for this one is a square hollow section. This is the section. The dimension of this section is, the circle diameter is 150 as well, and the thickness is 5 millimeter. Okay, so now we'll turn back to the paint to explain this one for you. So now question 2. For question 2, again we have simple beam. The height of this beam is 1.5 millimeter, and the load we have is Q equal to 10 kilonewton per meter. This member A, B, C. The span of this beam is 2 meter. And as we mentioned that the cross section of member AB okay, is a square hollow section. Okay, that's better than last one. And the dimension for this one is 150, and the thickness, this thickness is 5 millimeter. Okay, so this means that the outer given to us 150 millimeter, and the inner will be 150 minus 2 multiplied by 5 give us 140 millimeter. So the inner dimension is 140 millimeter. Okay, the requirement is to find maximum tensile stress in member A, B. Okay, to do this or to solve this problem, first of all, we need to know the straining action or the forces, internal forces in member AB. This means that we need to find the normal force N and the moment M. Okay, so we will deal with this as the simple beams we deal with before to find the normal and moment. Then the second step is to find the stress due to normal force and stress due to moment to find the combination stress or the combined stress. Okay, so now for the first step, N and M, we need to find the reaction and the moment and normal. What is the reaction we have here? Here we have hinge support, so we have XA and YA. And we have a link member. If we cut in this member, so we will have force FBC. Okay, so if I remove this part or just deal with this part, because we only need to deal with member AB, so we will have FBC, and we have uniform loads Q equal to 10 kilonewton per meter, and we have reactions XA, YA, and here FBC. But to find the reaction, we need to subdivide or find the components of member ABC. Okay, to find the components of member AC, if this theta, so this will be theta, so this is theta. So the horizontal component will be FBC, near component, so cosine theta, and here FBC sine theta. And to find theta, this is the triangle of theta, this 1.5 and this 2 meter. So theta will be 10 minus 1, 1.5 divided by 2, give us the angle theta, 36.86 degree. Okay, so now we can find the reactions. And before we find the reaction, we need to concentrate the uniform load. This 2 meters, so 10 by 2 will be 20. And now to find the reaction, we need to apply summation M at A equal to 0. Or I will start with some sigma M B equal to 0. So if we take the moment at this at B equal to 0, what cause moment at B? What cause moment at B is YA, sorry, multiplied by 2 and negative because it's rotate in clockwise direction, plus 20 multiplied by 1 give equal to 0, give us that YA should be 10 kilonewtons. Okay, if we apply summation Y equal to 0, so we have YA plus FB sine theta, but this should be negative because this is upward, this downward, minus 20 should be 0. This gives us that, and we know already, before I substitute, we know that this YA is 10. This give us FBC equal to negative 16.67 kilonewton. What this sign means, the negative sign, this sign means that our assumption was not right, and this force is compression force. So I will remove the arrow here. This force is compression. Okay, so now we find the force FBC. So the last step is to find XA. So if we apply the equation summation Fx equal to 0, again here, this is XA, Q equal to 10. So this FBC cosine theta, FBC sine theta, and this is theta. And we have here 10 kilonewtons. So we have XA minus FBC cosine theta should be 0, and we have FBC negative 16.67, so this gives us XA equal to negative 13.33 kilonewtons. This negative sign means XA is acting to the left, not to the right, as we assumed. Okay? So the final reaction for this beam, this FBC equal to 16.67, and here we have XA equal to 13.33 kilonewton, YA equal to 10 kilonewton, and we have 10 kilonewton per meter. And if we divide or subdivide this forces, the vertical component is 10 and the horizontal component is 13.33. Okay, so now we know the reaction. The next step is to find N and M. As we said before, N is the force normal to the cross section. What is the force normal to the cross section here? If this member AB, this is our section, so XA and 13.33 is normal to the section. Okay, so the normal force in this problem will be 13.333 kilonewton. And because if we make any cut here, this force is pulling the section. So this means it is tension or compression. Tension. If the force is pushing, so compression. So this force is positive 13.33 because it is tension. Okay. For the moment, how can you find the moment? If we have simple beam like this, and we have a uniform load Q equal to 10 kilonewton per meter square. So as you know, the moment will be a parabola from second degree, and the moment M will be Q L square to multiplied by 8 equal to Q is 10, L is 2 square divided by 8. This gives us that the moment is 5 kilonewton meter. So this is our moment. So now we knew that we have a moment equal to 5 kilonewton and normal force is 13.33. The last step or the second step after we know the straining action is the combination stress equation. So we know sigma equal to sigma n plus sigma m equal to positive n by a plus or minus m x I x multiplied by y. I will for you, if this our moment, if this force q, sorry, if we have q kilonewton per meter in this direction, and this is the moment, if we make a cut here in this section, so this will be x-axis and this y-axis. This moment m will cause mx moment. So our moment in this problem is mx, not my, because the moment is about x-axis, sorry. Okay, so now our equation or our formula, positive n by a plus or minus mx ix multiplied by y. Before we substitute, we need these two parameters. A will be the outer diameter area by the outer square to the divided by 4 minus by the inner square divided by 4, which means by 4 150 square minus 140 square give us the area is 2278 millimeter square. For I will be Ix because it's circular section, so Ix equal to Iy equal to pi divided by 64 d outer to the power 4 minus d inner to the power 4 give us that I will be by 4 150 square minus 140 to the power 4, sorry, to the power 4 give us inertia 6 multiplied by 10 to the power 6 millimeter to the power 4. And now we can substitute in the formula. So sigma will be positive n, which is 13.33 multiplied by 10 to the power 3 divided by area 2278 plus or minus m, which is 5 multiplied by 10 to the power 6 divided by I, which is 6 10 to the power 6 multiplied by y. What is y here? What is y max here? Because we need sigma max, so y max. If we return back to our section again, this is our cross section. Okay, so this is our cross section, and this is x-axis, y-axis, and this is the moment mx, and this is the normal force n. So what is y? Y is the distance from the CG to the far point. This is y max, and this also y max. Okay, so here y max will be, we know that the section height is 150 millimeters, so 75. This gives us that sigma equal to positive 6 Newton per millimeter plus or minus 62.5 Newton millimeter square. So sigma 1 and sigma 2. Sigma 1 will be positive 6, positive 62.5 give us positive 68.5 Newton per millimeter square. And the other component, positive 6 minus 62.5, give us the stress is equal to 56.5 negative Newton millimeter square. So, as required, the maximum tensile stress for this problem is 68.5. Okay. Do you have any question for this problem? All good? Okay. Do you have any question in the whole class? Uh, if you want, I can repeat any part if you want.
It's all good.
Okay, thank you, Singh. Anthony, all good with you as well?